Hello APES team. In this screencast, we're going to finish up Chapter 5 and we're going to cover Section 5.3. We're going to talk about the different things that limit the growth of a population. First, let's review what a population is. A population is a group of organisms of the same species living in some geographic area. Think of the human population of San Francisco, for example. The way that the population is spread over that area is called the population distribution, and there are three types: uniform, random, and clumped. Clumped is the most common, and clumping is a sign that organisms are grouping together for resources, for protection, or to hunt together as a pack. Fish in the ocean are often found clumped together into schools. They do this for protection. The chances that one fish will be caught and eaten decrease when they're mixed in amongst other members of the same species. A uniform distribution is often found when organisms are territorial. Seabirds and shorebirds, for example, will build their nest far away enough from each other so they're not pecked by their neighbors. A random distribution is the most rare and is often found when organisms are fighting over some limited resource. The trees in this forest, for example, are fighting for limited amounts of sunlight, so they will grow wherever they can. Population size is determined by births and deaths, but also by immigration and emigration. Immigration is movement into an area, and emigration is exiting an area. Population change can be calculated by taking the number of births and immigration, which increase population, and subtracting deaths and emigration, which decrease population. We can also look at a population by breaking it down into age groups. Organisms that are too young to reproduce are called pre-reproductives. Organisms that can reproduce are called reproductives. And finally, organisms that are too old to reproduce are called post-reproductives. When we look at these three types of organisms, we're looking at the age structure of the population. In these graphs, each bar represents the population size of different age ranges, from 0 years to 80 plus years. It shows three different types of countries. The Democratic Republic of Congo is a rapidly growing country because it has a lot of young people. The United States is a slow-growing country because the number of individuals in each age group is roughly equal. And Germany is a negatively growing country because you have a lot of older people in that population versus younger people. Another way that we can look at a population is by looking at the percentage of individuals that are surviving or dying at any given moment. This is called survivorship, and if we look at survivorship over time, we create something called a survivorship curve. There are three types of survivorship curves. Type 1 organisms are organisms that die late in life. They tend to be K-selected species, and two examples are elephants and humans. Organisms with a type 2 survivorship curve tend to have a constant death rate over their lifespans. Birds are an example. Organisms with a type 3 survivorship curve tend to die earlier in life. They tend to be R-selected species, and plants, insects, and fish are examples. Whether you are type 1, 2, or 3 tends to correlate with the amount of parental care, with type 1 with the most parental care and type 3 with the least parental care. Where you find a population or its potential to grow, are determined by its range of tolerance. The range of tolerance are the physical and chemical conditions that population can tolerate or handle. Individuals in that population or different species might have different ranges of tolerance, and you'll find them in different places in the environment. In the diagram, it shows different marine organisms and where they prefer or tend to live based on their range of tolerance. This graph shows the range of tolerance in terms of temperature for trout, a type of fish. There's an optimum range of temperature in which the trout prefer to live. Outside of that range, the fish are stressed, and outside of that stressed range, the fish are intolerant and cannot survive. Resources in nature tend to be limited or finite in quantity. As a result, the environment will only allow a population to grow so big. Environmental resistance are the factors that limit population growth. Typically, one factor will limit population growth over all other factors. This is called the limiting factor principle. And in nature, it tends to be things like precipitation, nutrients, and sunlight. Different species have evolved different reproductive strategies in order to be successful. Some species are selected. They have many offspring, but provide little to no parental care. Other species are K-selected. They will have a few offspring, but high parental care. K-selected species also tend to reproduce later in life. No population can grow indefinitely. At a certain point, there's a limit called the carrying capacity in which the population can grow. The carrying capacity is determined by a balance between population growth and environmental resistance. There are two types of population growth. The first is called exponential growth and occurs when a population grows at a fixed percentage each year. Growth seems to be limitless, and we say that the population is growing at its biotic potential, the maximum population growth rate under ideal conditions. The other type of population growth is called logistic growth and occurs when a population is pushed towards its limit by environmental resistance. The graphs show the two different types of growth. On the left side is exponential growth, which creates what we call a J-curve. On the right is logistic growth, which produces what we call an S-curve. The top of the S-curve is the carrying capacity. A population can exceed its carrying capacity. This is called overshoot and occurs when environmental conditions favor a short-term population boom. This is not sustainable, however, and is followed by a population crash, also called a dieback. An example are occasional swarms of locusts that experience population booms, then subsequent crashes. Another thing to keep in mind is that the carrying capacity can change. It can go up and down. For example, if there is major damage or disruption to an environment, the carrying capacity can go down. This graph tracking the changes in a moose population shows how both carrying capacity can change and how overshoot and dieback can occur. This graph showing the growth of a sheep population shows how overshoot can occur, but environmental resistance will always push the population numbers back down under the carrying capacity. When we look at population sizes of different species over time, they tend to produce certain patterns that we call population curves. Some populations have a stable population curve. Their numbers don't change much and they tend to hover at or near the carrying capacity. Other populations have an irregular population curve. Their numbers change randomly or chaotically. They tend to be opportunistic species that take quick advantage of resources when they appear. Some populations have cyclic population curves. Their population sizes go up and down and up and down, and that keeps repeating. And finally, some populations have eruptive population curves. These populations experience population explosions and then subsequent diebacks or crashes. This graph shows the 4 different types of population curves for comparison. In nature, there is a minimum population size required to ensure the survival of a population. This is called the minimum viable population, and this is why we're so concerned with protecting populations of endangered species in the wild. Population density is the number of individuals in a given area. It's a measure of how tightly packed organisms are. We can divide the factors that affect population growth into 2 categories: density-dependent factors and density-independent factors. Density-dependent factors tend to be biotic factors that increase in severity with population density. What that means is that the more dense a population is, the higher the mortality. Examples of this are things like competition, predation, and disease. These photos show one density-dependent factor, disease, on a chicken farm in the left and in one Tasmanian devil on the right. Disease spreads much faster when populations are more dense versus when they're less dense. Density-independent factors tend to be abiotic factors whose severity has nothing to do with population density. The chances of survival or mortality do not change with population size or population density. These are things like fire, severe weather, or pollution. For example, the chances of survival of the squirrel shown here do not change with population size or population density. Another example is drought, whose severity does not change based on population density. And finally, when there's pollution like this oil spill, the chances of survival do not change with population density. An example of shifts in population size are deer in the United States. In the early 1900s, we destroyed deer habitat through development and agriculture. We also hunted deer uncontrollably. In the 1920s and 30s, we passed laws to protect the deer, and as a result, they experienced a population boom. And today, deer are causing problems like spreading car disease, getting involved in car accidents, and eating vegetation in our gardens. Humans are also subject to nature's controls on population size. I can give you 3 examples. First is the Great Famine in Ireland, caused by a potato fungus in 1845. Second is the bubonic plague that occurred in the 14th century. And finally, the HIV/AIDS epidemic that is currently still affecting us. This graph shows that HIV and AIDS are still currently affecting us, especially on the African continent.